Where is my, hold on, let me find the, why it's not showing here. Hold on, let me, why I cannot find the, let me try to find the, okay, here I got it. No, why it's not sharing? Okay, now got it. Hold on, okay, yes. So last class, we already started to discuss logistic regression. And logistic regression is for classification, okay? So always keep this in mind. And if you recall previously when we discussed linear regression, and linear regression is not for classification, okay? It's for the prediction of continuous value. Okay, and if you recall at that time, we also linear regression if you do polynomial. And sometimes for certain data set, it can fit better, is it? And when we discuss a polynomial example, we also show, but sometimes polynomial can also cause a concept, we call it overfitting, okay? So overfitting is caused by, so the data set, so that fits very well for training data. But when you have new data samples, then the performance going down. Okay, so that we call it overfitting. Okay, overfitting is because it does not generalize well to unseen data. Okay, unseen data. And then normally it can be caused like by, we call it a high variance. So there is another important concept is regarding variance versus bias. Okay, and if you recall, bias, when we discuss all of the models, the perceptron, Adeline, linear regression, and the logistic, we always discuss, for the net input part, we discuss the W0 and X0. X0 is always 1, is it? And W0, and we call that a bias term. Is it? So that's regarding bias. And variance, it's normally used to describe the spread out of the data, the samples, is it? And so if variance is high, that generally means that, and overall your sample also has some mean values, is it? So that means data spread out, so farther away from the mean values. And also the sample, the distance between the samples is also quite farther away. So that's why we say it's mostly the variance, if the variance is high, then that means of the samples spread out quite a lot. Is it because it's spread out? That's in our previous discussion, we said, oh, sometimes maybe polynomial that may better describe. Is it because for polynomial, maybe you also have collinear. You also have like the cross product of the features. Is it in your models? So then it can cause the high variance because you try to fit the training data. Is it training data? So it may have also another course may have too many parameters that lead the model too complex. Is it given the underlying data? Okay, so that's regarding overfitting. So generally speaking, overfitting is caused by high variance. High variance just means the data spread out too much. Okay. And then you pick the model may be too complex. So you consider too many features, or you consider like you correlate the features together. So that can cause high variance. So high variance, then it introduces overfitting. And the versus overfitting, it's underfitting. Okay, then for underfitting is your model may be too simple. It may be too simple. Maybe your model need a polynomial to model, but you just pick a linear one. And then that's too simple. So not complex enough to capture the pattern in the training data, etc. So then the performance is also going to be low on unseen data, as on unseen. And higher, generally speaking, underfitting is caused by high variance or high bias. Okay, so the bias, then you can, if you recall the net input, is it? So it's W0 X0 plus like W1 X1, is it? And of the features. So just think about if this term's value is very large, then definitely it will reduce the impact of the remaining terms, is it? So that's why it can cause the underfit, so higher bias. Okay, and how to tackle like the overfitting, later on we will see we can use a technique, we call it regularization. Okay, so in machine learning, that's one way to do the parameter tuning. So variance and bias, and we already discussed. Okay, so just keep in mind is high variance, it will induce to overfitting. And higher bias, then it will induce to underfitting. And to tackle overfitting, one of the approaches that we use is called regularization. And we have like L1 regular, L2 regularization, okay? And today we will see L2 regularization. Okay, and so we needed to find the balance between variance and the bias. So the trade-off between them, etc. So it says tune the complexity of the model, then we can use regularization. Okay, because it's a regularization is very useful to handle collinearity, is it high correlation among features. Okay, because there may be some correlation between features. Is it also good at filter out noise from data? And then it can prevent overfitting. Okay, and how regularization works is we are going to introduce an additional information. So basically, it's some kind of bias. And we said that we are going to penalize some weight values, extreme weight values. Okay, so for the L2 regularization, and sometimes also called weight decay or L2 shrinkage. Okay, so basically it's, we are going to add this term. So add it to the cost function, okay, to the cost. And so this is regarding all of the weight, is it? Then you square it. And this lambda, okay, it's called regularization parameter. So this one, we can adjust. We can adjust. Okay, so previously we learned like the learning rate. So learning rate is to find the best learning rate to make your gradient descent, to converge faster. That's regarding learning rate. And this lambda is called regularization parameter. Okay, so we can adjust it, because just think about, if you pick larger values, that means you are going to add more influence of the weight overall. So this is regarding all of the weight, is it? So you square each individual one, then you sum all of the weights regarding each of the features, that you add all of them together, okay? And then we add them to the cost. But if you recall previously, for gradient descent, our goal is to what? Is to minimize cost. But here you add another term to the cost. So you purposely manually increase the cost. Is it to increase? And then, of course, it will impact the original cost function. Is it? So that's how it can regularize, okay, our learning. So it can reduce the overfit. So then for logistic regression, the regularization, then it says add a simple regularization term, is it? So that's the term that we just saw, okay, we just saw. And this part, we already saw it last class, okay, last class, if you recall. And the goal for logistic is to maximize the likelihood, is it? And this is the cost function, is we take the log, is it, for the likelihood. So that's how we come up. And then we try to minimize our cost, okay? And previously we never saw this term, is it? But now you add this regularization term to the cost function. Then you just think about it, is it? So it's manually increase the cost. Then it's squeeze this part's impact, is it? Impacts. So the value later on in our example, we can also see, is it? If you increase this lambda, then you increase the regularization strength, okay? And in sklearn, package, we use a parameter, we call it C, okay? We're not going to directly use the lambda in sklearn. We use a parameter called C. And the relationship between C and the lambda is 1 over C. So C is inverse. Okay, C is inverse. So if you want to increase the regularization term, then you need to decrease C. Okay, then lambda, then it's increase. So just be careful about the relationship among of this new ideas. Okay, and what next before we move on to our example? Another thing in our example we are going to see it's regarding like models performance. Is it your models performance for machine learning models performance? Previously, we said we measure the performance using accuracy. Is it? So accuracy is so how many you predict correctly among all of the provided testing samples. Is it? That's regarding accuracy. But a lot of time, if you just use accuracy, that may not describe the case well. Okay, the case well. So we use another one, we call it confusion matrix. Matrix. Okay, so the confusion matrix is as a summary prediction results on a classification problem. Okay, so this is for classification problem. So it's a matrix. So basically there are two rows for this matrix. So over here we discuss the binary classification. Okay, class 1 and class 2, etc. And the column is for predicted. So this is the actual. The row is regarding actual. The column is regarding predicted. Okay. So the first cell, then this is true positive. So P is positive, N is negative. Okay. And then this cell is represent false negative. Okay, false negative. And then this cell is false positive. And this one is true negative. Okay, so that's regarding the confusion matrix. And with the confusion matrix, the accuracy that previously we used, basically you can also find the accuracy with the confusion matrix. So it's true positive and true negative. So two diagonal values, you add them together. Is it over, you add all of the values together. So false negative and false positive. So this is accuracy. But with confusion matrix, like over here, say if you just use accuracy, there are some problems. Okay, it even though 99 accuracy, then it cannot, you cannot just say it's excellent. It may be also a terrible, okay, terrible model. Okay, so some other performance matrix that we can use from the confusion matrix. The first is called recall. Okay, so what is recall? So recall is a ratio of true positive versus true positive add the false negative. Okay, so if recall is high, if it's a high recall, then that means this number is small. So of course, this also is a plus, is it? So this is another one performance matrix. And the next one is called precision. Precision. So precision is true positive over true positive plus false positive. Okay, so if this number is high, then that means false positive is small. So it's also a good sign. Okay, so over here, we also discuss some scenario, is it? So you may have high recall, low precision, is it? Then if you have low precision, then that means this number is large, is it? Is long. But of course, you do have pretty good number because you have high recalls, is it? So then that means most of the positive examples are correctly recognized. Okay, so that's what this cases mean. And you may also have low recall and high precision, is it? Then that just shows you miss a lot of positive examples, is it? But what you predict, then they are indeed positive. Okay, so that's regarding this scenario. There is another factor that you can use. Matrix is called F measure. Okay, so F measure, then to consider both precision and recall together, and we try to use the harmonic mean, okay, to represent instead of just the heuristic mean, okay, to punish the extreme values, okay. And then that's the F measure always near to the smaller one of precision or recall. Okay. And in sklearn, they also provide this the matrix regarding the metrics regarding all the recall precision F measure. Okay. So next, let's first take a look of an example. Okay. Where is my hold on, okay, let me find the where is it? Cannot find it. Oh, it's here. Okay, so next let's continue our previous class discussion, and this example it's still from that chapter 3, okay, that sklearn. So that's regarding that iris flower classification one. Okay, so regarding, if you just quick recall, it's regarding the features regarding petal width, length, and the saddle width and the length, is it? And then we predict which kind of flower it is it? And last class, we already saw our logistic regression model using it, is it? Let's first see. Yeah, let's first. So here we just continue our previous logistic regression. Okay, but over here in this part, we are going to collect as we are going to change the regularization. So that regularization coefficient, okay, parameter. So we are going to change it. Let's say we are going to change it. So it's 10 to the like a -1, 10 to the -4, 10 to the -3, 2, all the way like 1, and then 2, 10 to the 5, is it? Within this range, the C value with different C, then let's see how the result is going to be, is it? So we are going to change this. So we call logistic regression, but within the loop, each iteration, we use a new regularization parameter. Then we fit our model, is it, with the training model. And then we collect the weights first here, okay? So the weight you can collect is from the logistic regression, the coefficient. If you recall the interception, the coefficient is that you can collect them. And we can also collect this parameter, the regularization parameter, okay? And we also collect the predict, then we find the accuracy score, is it? And we also keep track of the scores, and we store all of those in Python list, okay, in Python list. And then we do plotting. So what next part try to show is just do the plotting, okay, on Python, the PyPlot, okay. So the plot, what we first draw is regarding the weights, okay, regarding the weights. And then let's see the weight versus the regularization. So then you can see it does impact the weight values with the change. Is it with the change of the C values? With the change of our C values. So here is C, is it? And here is the weight, W, is it? And we pick regarding paddle length and paddle width, is it? And we can clearly see the weight values change, is it, for both paddle length and paddle weight with the change of this regularization value. Is it? If weight change, then definitely it will impact your model, the performance. So next, let's also see. Over here, we print out, okay, the C values and the accuracy, okay. So we can see the C value is quite small, is it? So that means what? That means lambda is quite large. And lambda is large, that means if you recall, it's lambda times that W, is it? So then this part is going to be very large. So it's a kind of the bias, is it? So that's why you can see the accuracy is quite low, is it? Only when you see, when the C value is 1, is it? When the C value 1 is, the accuracy is over 90%, is it? If C is very large, then that means lambda is very small. If lambda is very small, then definitely this term is going to be small. So it's kind of like you drop this term, is it? So it's the original. And for these cases, okay, for this ARIS data cases, looks like the C value is large, is good, is it? So the regularization we can see in this case doesn't play a role for increasing our model's accuracy. Is it because why? Because in this case, the model itself is not that comprehensive because there are only a couple of features that here we consider. Okay, and then the next one, what we draw is we are going to draw the accuracy score versus the C value, okay? So the plotting, let's take a look. Is it? So from this plotting, you can clearly see, is it? With the decrease of the C value, the accuracy dropped a lot. But with the increasing of the C value, the accuracy didn't decrease a lot. It's still above 90%. So it's quite good. So what this just means that this new regularization term doesn't play a very important role in this model, okay? Okay, so that's regarding this example. And what next we are going to see is, we are going to see this example. This example, so in machine learning for image classification, and this is called digit. okay, classification. With the handwritten, okay. So the digit is 0, 1, 2, all the way to 9, okay. So 10 digits, is it? And so over here, so this this handwritten digit data set, this is a very classic example, like using machine learning to do image classification, okay. And this data set is, we call it MNIST data, okay. And it's over probably 70,000 handwritten digits, okay. And each digit is 28 by 28 pixels, okay. And over here, we are going to use a logistic regression, okay, to do the image recognition. The first example regarding the handwritten digit, we just, the sklearn data set also has the data set. And this version is a low, it's not a high definition. So it's not the high definition, it's very low. So it's 8 pixel by 8 pixel. Okay, very low one, okay. So we also see the data shape. So, and the total number of samples also not a lot, it's just around 1,700-ish, okay. And the target value, then it's 0, 1, 2, there's those 10 digit, okay. The training data, what is the training data? You can see for each sample, it has 64 features. And how this 64 features come from? It comes from because the image is 8 by 8 pixel. It's a pixel. So that's how it comes out. So we flatten it as 64 features, because each pixel in image is represented by a color value RGB as 0 to 255, is it? So that's how we have this 64 features, okay? So basically it's regarding each pixel. And then you can see, then with the machine learning, with the very comprehensive images, then it's going to be so the features, just think about it, how big it's going to be, because it features regarding each pixel, okay? But anyway, here just let's get some very basic idea. And then we can also show those handwritten images. So all this, so you can see it's quite low definition. It's not high, it's not very obvious. It is for those handwritten digits, okay? And we can use the pie plot, the image show, to show the handwritten original image. So over here, we pick the first 5 samples, okay, first 5 samples, and we do the subplot. So we have 5 subplots, 5 plots. And for each of it, then we are going to show the corresponding image, okay, the handwritten image. And here, that's the original one, Okay, so anyway, so that's regarding the original image. And over here, then we first do is split the data into training and testing as usual, is it? And then you split a certain percentage. And then next, we just use logistic regression, okay? And over here, we just use the default values, okay? The parameters, like the C value for the default, it's 1, I remember, okay? The regularization. And then we do the model fit, is it? After that, then we can test. So this is the first testing data, and this is a predicted one. And we can also see the result. It's recognized 2, is it? It's 2, number 2. And then what next to try to show is within the testing data, we take the top 10, we do predict, okay? And then to see if they are the same as the original testing digit, is it? And you can see it's all true, is it? So all predicted correctly. So looks like logistic regarding this handwritten digit, the result is pretty good, is it? And then the overall accuracy score, it's 95%. This is pretty good. And what the next one try to show is, so pie plot we already kind of see, is it? There is another plotting tool, okay? This is also quite nice. It adds a lot of aesthetics, so beautify your plotting, okay? So Sept, okay? So it's a package also for plotting. Okay, and over here, we're also going to import the performance matrix from sklearn. And previously, we discussed the confusion matrix, is it? So over here, we want to see for our handwritten digit of the digit data set, is it the confusion matrix regarding the testing data, is it, and the prediction. Then we can, because we already have prediction testing, is it, and we want to see how overall the performance it is. We can clearly see the confusion matrix. So the confusion matrix, if you just call it, it will give us this result, is it? And this is confusion matrix, so this is digit 0, digit 1, digit 2, all the way to digit 9, is it? This is 0, 1, all the way to 9, is it? And this is, the column is regarding predicted, and the row is actual, is it? And you can see for digit 0, looks like there is no wrong predicted. Everything is correct, is it? And then for 1, you have this 2 not correct. And here you have wrong, and here you have wrong. So the confusion matrix gave you a lot of more detailed information, is it, about all of your predicted values. So where the wrong predicted values happens, is it? Where the offset of the actual value and the predicted value comes from. Okay, so this is regarding confusion matrix. And what's next one? So today we also see another nice feature is regarding heat map. Okay, we are also going to draw a heat map regarding this confusion matrix. Okay, and the heat map is quite useful. Okay, it's quite helpful. Generally, it's used to describe. So it's kind of you have a grade a grade, okay, and this grade is regarding some features, okay, so it's regarding something that you're going to measure, okay, so we have kind of x-axis and another axis, is it? So anyway, so some variables. So you want to describe the relationship between these two, but the heat map is with the change value of like variable 1 and variable 2, is it? So it's involved the third dimension. So heat map is it's kind of like, if you recall the topology, that in gradient descent, that when we discussed, is it like the cost? Is it the cost plotting? That topology, is it? So it's, and over here, it's not going the third dimension. The third dimension, it's not going to use some number to represent, is it? It's going to use color to represent kind of the third dimension, okay? So over here, what we are going to describe for this confusion matrix heat map, and if you recall, if you, let's take a look, is it? So what it describes is the horizontal represent predicted label value 0 to 9, is it? And the vertical are the actual label 0 to 9. And the side, we have a bar, the color bar, is it? And the color bar, it has some number, is it 0, 10, 20, 30. So basically over here, it's represent the number of the actual and the predicted match with each other. So it represents correctly predicted numbers, is it? So the darker color, is it? So darker color, then over here just means 0, is it? The number. And the lighter color, in this case, represent a larger number. So this darker color represents small number in this case. But in a lot of other cases for heat map is not just used for confusion matrix, it can be used for a lot of cases, other cases, okay? And in a lot of other cases, you will also see heat map generally larger number. It's for, it's dark color. Dark color, is it? And if you recall, a lot of COVID cases map, is it? The color map, basically, it's also kind of the heat map, okay? But a lot of times that's regarding like the US map, is it? And certain ranges, hot spot, is it? With darker color, okay? So anyway, so that's regarding the heat map. So over here, we put our confusion matrix with the heat map, is it? And then you can see, is it the light color over here? It's all predicted correctly, is it? And we can also see the dark color here, is it? So that means predicted wrong, is it? And the numbers you can see is quite small, is it? So from this heat map, we can also kind of conclude that our model doing pretty good in this case, okay? So over here, we already see the heat map, is it? So heat map, if you want to use, you can use Sepp's heat map, okay? Then here it's that confusion matrix value that you plug in, okay? And you can also specify the color map. Okay, so this is for color map. And the C1 itself is also, there are a lot of stuff. Okay, so if you are interested after class, then you can try to find more material regarding CBOM. Okay, it's quite helpful. And you can see it helps us to do also a lot of coloring work. Okay, so that's regarding the confusion matrix and heat map. What the next one try to show is, in this case, you can also find all of the misclassified index. So which sample is wrong, etc. So a lot of case you also want to find out is why it is wrong. So locate the exact sample, etc. So then here you can borrow this to do that. And what the next one I'm trying to show is with the MNIST. Okay, the MNIST, the data size basically it's about 70,000. Okay, 70,000, and the image pixel size is 28 by 28. So because the pixel is more, so definitely it's more clear, etc. And we can also get the MNIST data directly from sklearn. Okay, the fetch open machine learning. Okay, so fetch open here, and then you specify this MNIST 785. And the MNIST, you can also get it from a lot of other places. Okay, so over here, we just directly import it from the sklearn. And we do test and training, etc., split. And here, same thing, we do the image, show image, etc. And here, clearly, you can see it's much better than the previous example. It's with more pixels, as you can see. This is regarding the pixels. So then in this case, the pixel is 28 by 28, is it? And then the number of features, is it? It's 784. It's also quite large, is it? So that means you're going to have 784 columns, is it? For the data set with the row and the column, is it? So you have 784 features. Okay, be careful here for image. We can see it's quite large. So then when you do training, just think about it. Is it? Then you need to have 784 weights. Is it? To train, to find the optimal one. So the job is quite large. Okay. And if you recall previously, we also discussed feature scaling. Okay, and for feature scaling in sklearn, you can directly get it from pre-processing, is it? And you do feature scaling, so standardize, normalize the data, is it? And then you transform your data so that the range can be between 0 to 1, is it? Something like that. Okay, so that's regarding feature scaling. And then what over here we are going to do is continue going to do logistic regression. Okay, and for logistic regression, you can also sometimes the default number of iterations is 100, and sometimes it may not be able to converge. Okay, so in this case, you can specify your own number of converging iterations for your model, okay, to stop. And then you can do the fit, that with the training data, okay. Then we can also predict. And for this predict, if you recall, this is regarding the probability. Because logistic regression is more associated with probability, is it? So the predicted probability for 10 digits. So this is for digit 0, digit 1, digit 2, is it all the way to digit 9. Then you can clearly see the first one, the probability is the highest among all of them, is it? So that's why this first one, then the digit is digit 0, okay. And yeah, and that's all for this year. So basically, we finish the logistic